Hi, everyone. Thank you for joining us for our next live stream. I'll be your producer for this session. Before we start, I do have some quick housekeeping. Please take a moment to read our code of conduct. We seek to provide a respectful environment for both our audience and presenters. While we absolutely encourage engagement in the chat, we ask that you please be mindful of your commentary, remain professional, and on topic. Keep an eye on that chat. We'll be dropping helpful links and checking for questions for our presenters to answer live. Our session is being recorded. It will be available to view on demand right here on the Reactor channel. With that, I'd love to turn it over to our speakers for today. Thank you for joining.
Hi, everyone, and welcome. Thank you for joining us today. I'm going to be doing the first talk of this session and then handing it over to Newton for the second half. And I'm going to be talking about AI beyond English, so building multilingual AI solutions. Before I dive in too deep, I want to give a brief background and introduction for myself. I have been in consulting for a while now as a data scientist at a big firm. Prior to that, I did my PhD in astrophysics, did a lot of coding and data analysis and modeling, which got me into the data science space. Since being in industry, my focus has been primarily natural language processing problems, and in particular, building custom NLP solutions for big Fortune 500 type companies. And as part of that, I nowadays, of course, NLP means Gen AI and LLMs and agentic AI, and that's a lot of what I do now, day to day. In addition, I took all of my knowledge and lessons learned from my previous work over the past decade or so, and I wrote a book about it. So that book is called Teaching Computers to Read, and the content today is coming from one of the chapters in that book about building multilingual solutions. And it also has a code companion. So if you're interested, feel free to Google it. It's on Amazon as well as CRC Press, which is my publisher. So that's a brief background on me. And now I will dive right into talking about NLP and languages. So I'd like everyone in the audience to take a moment and think of a natural language processing use case. It could be one you've come across recently. Maybe it's a help desk chatbot that you interacted with. Maybe it's just working with an LLM to write something in your style and your voice. Or maybe it's a customer call routing system when you were calling to make an appointment. Or maybe it's something you built at work. Maybe it's something you did as a side project. Or maybe it's even just an article you read recently. But think about, giving you time here to think about an NLP use case you've come across recently. So think about that use case for a minute, what it does, what unstructured text it deals with. And the next question I'm going to ask is, what was the language that you were thinking of? Now, I can't actually take a poll of the audience, but the last time I did this, most people were thinking about an English use case, which is pretty normal. Where I'm in the United States, I'm in Seattle. English is my day-to-day. So when I build use cases for clients across the United States, I'm also almost always working in English. But it tends to be the default when we think about natural language processing, when we think about large language models. English is kind of just always the go-to, whether we say it or not. And there's nothing wrong with that inherently, but it's important to be cognizant of it. And there's a professor at the University of Washington, Professor Bender, Dr. Bender, who has this rule called the Bender rule, which is that we should state the name of the language that we're studying, especially in research, and even if it's English, acknowledging that, if we're doing research in a particular area, if that research is in English, it's worth calling that out. If it's in another language, it almost always gets called out, But if it's English, it doesn't always get called out that, hey, this research was done in English. If we don't say what language we're working in, then it kind of, as she says here, gives a false veneer that the research that we're doing or the work that we're doing is language independent, and it's going to work just as well in French or Somali or Korean as it does in English, which probably isn't the case. So that's some of what we're going to talk about today, which is how working in different languages can be challenging, but also just being aware of some of those challenges and how that can impact the decisions that we make about our data. And one additional thing I'll call out here before I move on is that when you go and look at the research papers, the literature, as well as looking at the benchmarks that we see for LLMs and kind of each new iteration and release of a new version of an LLM, those benchmarks are largely in English. And there is kind of that bias when we look at the research and when we look at the work that's being done in natural language processing and in the AI space right now. So, which leads us to the question, why does it matter? There is this inherent bias that a lot of work is being done in English, and that's true kind of across the board for different types of NLP research. But why does it matter? And I'm hoping that I can drive this home to all of you watching with the two plots that I have here. So if you look at the top plot, this is the data that's accessible on the internet. So if we look at the breakdown of data across languages for the top 10 or so languages on the internet, it is heavily English. English is almost half of the data on the internet, which is a huge, like overwhelming majority compared to all of the other languages at much lower percentages. And of course, it only decreases from here. However, when we look at the bottom plot, what are the languages that are most spoken? English is still at the top there, but it's not nearly as skewed, right? So when we think about the top plot, that represents the data, but the bottom plot represents reality of what people actually speak and work in day to day. And there is a big discrepancy here. Not only because the bottom plot is much less skewed, there's a much more variation in what people speak day to day. But in addition, if you look at the specific languages that are in the top plot and the bottom plot, there's actually not a lot of overlap. There's a little bit of overlap between the languages, English, Spanish, etc., but there's a lot of differences too. And what this means is that the data that we're using to train large language models is mostly English, and it does not necessarily represent very well the languages that are spoken across the world. And so that disconnect means that large language models are going to work best in English because that's what they're seeing the most data during the training process and the building process of large language models. And that's a bias we all need to be aware of, especially if you are a non-native English speaker, if you're commonly using other languages in your day-to-day or your work. It's important to be aware that, this is built on English data primarily. And the more people use LLMs for everything in the AI space, the more this can negatively impact people who are not using English in their day-to-day, or just have use cases for languages outside of English. So this is really important. If you take away nothing else from this talk, I hope this is a takeaway for you. But I want to move to a specific example from my own work. I've been lucky enough to work across a few different languages in my time. So I wanted to bring forward one particular example from my work, which is extracting information from documents. It's a very common task. I work with a lot of finance teams and procurement teams. They have hundreds of thousands of PDF contracts. They don't know what's in them. So a common task, as an example here, is to extract start and end dates from contracts. So I have an example here in English where we want to pull out the effective date and the expiration date. Nowadays, with our kind of modern era of tools, this is pretty straightforward. If it's a PDF that's not machine readable, I'm going to run OCR to get the text out of the document. I'm going to run language detection to confirm it's in English. I'm going to tokenize the words and sentences, embed those, and then do a pretty basic RAG retrieval with a prompt and an LLM. And with that, I'm going to get those dates out and I can format them to month, day, year format. Pretty straightforward. But in other languages, this is not as straightforward. So a few years ago, and this is just an example document. This is not actually a Japanese document, but I was unable to find a kind of open source version. So you'll have to bear with me as this elucidates my point. But I was working with colleagues and with a client in Japan, and all of their contracts were in Japanese. So the character set is very different than the Latin character set that we have in English. And in addition to that, their contract end dates in particular were in these stamps. And again, this is not a perfect example, but the stamps kind of looked like this. You have this round stamp and there's a date written in it. So that by itself is already more challenging. You have very different characters. You have kind of machine readable text that you have to parse out from the image from that stamp. And in addition to this, in the contracts that we were working with, the end date was not what I think of when I think of a date as month, day, year. Instead, the date was noted as what is the emperor era, what is the year within that emperor era, and the month and day within that emperor era and year. So one of the things that happened in 2019 during this project was that the emperor actually changed in Japan, which meant all of the old dates, expiration dates, were listed in an emperor year of that emperor era that would no longer exist because the emperor changed. So we had to figure out what the dates were in the old emperor era and then translate that into what the new emperor era year, month, and day would be, which is very complicated. In addition to just the standard NLP things that we have to do to get text out of a document and parse it, there are all of these layers of complication on top of that. So this is an example I always go back to remind myself that things are not always easy when we're working with languages outside of English. And it's really important to understand what the specific challenges are in the languages that we're actually working with. So with that example, kind of bringing it back to what makes data science outside of English more difficult. And this is not exhaustive, but a few things that make it more difficult are having non-Latin characters. Again, when we think back to the data, most of the data is in English and other Latin-based languages. In English, we have about 26 letters plus punctuation and numbers. It's not a lot of characters, and they're very well represented in the data. Other languages, however, like Japanese and Chinese, you can have thousands of characters. And so the more characters you have in a language, the more complex the analysis and use and understanding of those characters are. In addition, in those languages, as well as some other languages, a character could be a letter or a word. So in English, we think of a letter as A, B, C, D, and a word is generally a combination of those letters. But in other languages, you can have a single character that could mean just that one letter, or it can mean an entire word, which again makes it the parsing and understanding of the language more difficult. And then we already talked a little bit about the data availability piece. The less data there is available in the language, generally the tools are not as good at understanding and parsing and analyzing that language. That kind of goes hand in hand with the popularity of that language in data science research. Again, English far and above the most popular language for research in the data science and AI space. But other languages are also have some popularity, but not as popular. And there are plenty that get completely ignored in the research. And the research leads to the technology advances, and it leads to the tools and technologies that we all use as data scientists or AI engineers on a daily basis. And then there's the specificity of the domain. So the more specific language you have in like the medical realm or the legal realm, that also makes it more difficult. So it's, again, kind of another layer of difficulty on top of working in another language. But the general takeaway here is that the further you are from English, the harder it is to get high performance for a solution that you might be building. So the more non-Latin characters that you have, the more characters in the language you have, the more complicating factors, the harder it is to get high performance. It's not a hard and fast rule, but generally the more different the language is from English, the lower performance that we get kind of out of the box with a lot of the tools and technologies that are out there. So the question then becomes, how should this impact what we build and what we do in the AI space? And my mantra always comes back to really picking the right tool for the job, and in this case, picking the right approach for the data that we actually have. And so this comes back to understanding what is the data that we have and understanding our data distribution and the language distribution in that data. So I kind of have this branching out, and I'll walk through the different branches here. So if we start on the left side, this kind of the monolingual side. So you just have a single language in your corpus of data, And that's really all you're ever going to see is that one language. And this might be something we just know based on the area that the data is in. For example, if I'm working with a healthcare company that's in the US and they only operate in the US, then their data is pretty much only going to be English. But that might not be true in other cases. But if we know and have some knowledge that our corpus is only a single language, then there's really two options. It's either entirely English or it's entirely some other language. So if it's entirely English, then great. In the US, the majority of the time we're here. It's one language, it's English. Again, easy peasy. All the tools are optimized for our use in English and English only. Now, if it's another language other than English, that still makes it a little bit easier than if we have a bunch of different languages in our corpus. And we can optimize our solution for that language. We might encounter slightly different challenges. We might have overall lower performance than if everything was in English, but at least we just have that one language to focus on. And I've done this a lot in my work, working with just Thai language data, or in a different project, just the Japanese language data, and then French language data as well. And those are all a little bit easier because at least you're just, again, focused on that one language. Now, on the other side of the diagram here, we have the case where we have multiple languages in our corpus. So we might have English, but we might have 10 other languages in addition to English. And in this scenario, there's kind of two main approaches that we can take. And there's a few factors that I'll talk about a bit later to help decide what's the right approach to take here, considerations, if you will. So one approach, if you have multiple languages in your corpus, is to build kind of individual pipelines for each of those languages. The benefit there is that you can optimize each of those pipelines to maximize performance for that language. But as you might already guess, the downside is that takes a lot more time and energy. If you have 15 different languages and you're building 15 different pipelines, I don't usually get the budget for that. I don't know about you all, but there is the benefit of having higher performance. Now, on the other side here, another option is to translate everything. And usually this means identify what language your document in your corpus is coming into, identify that language, translate it to English, and then you have a single pipeline in English. It doesn't have to be English, it usually is, but you could have translate everything to French and then do the whole pipeline in French. This has the benefit of being a lot easier. You kind of just have the one main pipeline. But again, the downside there is the flip side of the other option, which is performance tends to be lower. Again, the more similar languages are to one another, the easier the translate everything approach will be to give you better performance. But if you have very different languages, then that kind of single pipeline approach where you just translate everything into a single language is not going to work quite as well. You can also take a hybrid approach where, one thing that I've done in one of my projects, working with a global healthcare company, they had inquiries coming in from all around the world from consumers using their products. But most of those were in English and about 3 other languages. So for those, we did build individual pipelines for those 4 languages, and everything else, which had very, very low data volumes, we just translated into English. So we kind of had like 5 pipelines, 4 for the 4 high volume languages, and then another one to translate everything into English and then push it through the English pipeline. So you can take this hybrid approach. And again, it depends on what data you have. So are you seeing massive amounts of data in 20 different languages, or are you seeing most of your data clustered in 2 languages? That's going to impact the approach that you want to take here. So with that, I did want to talk also about a few common pitfalls that we see when working outside of the English language. One is language identification, which seems like it should be straightforward, but it is not always straightforward. I'll talk a little bit about data types and conversion. I already talked a little bit about language volume and representation. Just know that, again, that's a common pitfall. And then talk a bit about processing and evaluation before wrapping up. So language identification, again, seems like it should be straightforward. You get a document in from your corpus and you figure out, well, which languages it is. And there are you can do this with an LLM, but there are great APIs out there that do language identification and translation, and that's what they're designed for, and they do a great job. There are some keys that help to more easily identify the correct language for the language identification step. Things like unique characters. So one of the characters here in Chinese and kanji, this character means word, but that's something that really only shows up in those languages. So if you see that, then you know you're probably working in one of these handful of languages. And similar with the O slash, which is pretty much only used in Norwegian. So again, if you see that, you're likely in a Norwegian language document. So some of those clues of very unique characters are helpful to more confidently identify what language it is that you're seeing in your document automatically. Another tool for that is high probability words. So again, there are words that you don't really see aside from proper nouns that you don't really see in other languages. And so there's a couple examples here in Dutch for the word it and Polish for the word all. Those are both very common words. So if you're seeing that a lot, you're probably in that language. And those also help to uniquely and confidently identify what language you're working in. Another one I want to talk about is volume and consistency. So the real challenge here is that you don't usually, or I shouldn't say usually, but you don't always get documents that are a single language. I have often in my work seen documents in a corpus that have multiple languages melded together in them. You see this a lot with social media posts, but you also see it with more kind of standard documents like PDFs or even emails, where you might have, actually just today I got an out of office message from someone that had their English out of office and then their Portuguese out of office, one after another. It says the same thing, but there's two different languages in that auto email response. And so the amount of data and the consistency of the language of that data, the more you have of that, the easier it is to identify with higher confidence that this is the language that's there. So for example, if you just have a 3-word sentence, it's a lot harder to confidently say it's this language A instead of language B, as opposed if you have 3 whole paragraphs that are consistent in that same language. You're much more confident about saying, yes, it's this language. And then I already talked a little bit about language mixtures, but you know, there's some corpus that have mixed documents, and that becomes normal. So the example here is, I love donuts, but I hate coffee. And like, what do you do with that if you receive that and you have to analyze it? And that's where the challenges come in with language identification. There are some things that make it easier, but then there's also some of these things that make it harder. And really, it's like, what do you do in those cases? And again, it goes back to understanding your data. How often is this happening? Is this an aberration, or is this something we're seeing, this mixed languages, for example? Is that something we're seeing consistently throughout our data? So it's important to understand that, and then also understand, what are we trying to do with this data? And then you can kind of take an approach of, again, do you translate everything within a single document? If it's mixed languages, you translate that all to one language, or leave it mixed and only focus on one of the languages that might be present. There are different approaches you can take, but it depends on what the outcomes we're trying to get to are. So I want to talk briefly about data type and conversion. It would be nice if we always had machine readable text across our corpus. I would say I have not found that with any of my clients that I work with yet, which means we always have to do some type of data conversion. This means we might be getting PDFs, we might be getting images, we might be getting audio, and we have to get that into a kind of raw text format that we can then process and analyze with our models. So surprise, surprise, this is also more difficult for non-English languages for some of the reasons that we've already talked about. You know, cases where there's a lot, hundreds or thousands of individual characters in a language, that makes it harder to classify, both in OCR and in audio transcription. But then there are other things like text orientation on the page. With audio, you obviously have accents, dialects, tonal languages, among many other factors. So just getting your raw data into text, it can often be even more challenging outside of English. So I have a brief example here that I'll show, and this is an OCR example. So if you look at the top row here, let's pretend we have a PDF and we need to OCR it. So if the original text in the PDF says, he went for a drink of water in the kitchen, but maybe the OCR made a mistake. So if you go down to that second row, maybe it, you know, the pixels weren't quite right around that E, so it thought it was water instead of water. Now, in English, that's fine. We know water is not a word, and we know from context that it must have meant water. So this is easy enough to correct with a kind of a post-processing or even just pure probability-based correction for the text that we're extracting from the document. However, in other languages, again, not surprising here, more difficult. So in this case, if we look at the column of Japanese text, again, you have your original sentence in the document as that top example. And then again, let's say there was an OCR mistake. Some of the pixels weren't clear in the image. So when we OCR it, we mistake a character. So that character is two very different words, even though it's only a few pixels difference. So that small difference in pixels means a very big OCR error. Because this character is also a word, we've now messed up the meaning due to the OCR, and now it says I bought a fresh claw at the market instead of the original text, which was I bought a fresh melon at the market. Both very reasonable. Maybe it was a lobster claw, I don't know. But those are both valid sentences, and it's because of just a couple pixels that we got that wrong and we got the meaning of the sentence wrong. So this is just an example of some of the challenges that we see in the data type and data conversion with other languages that we don't see in English necessarily. So on a similar note, when it comes to processing non-Latin characters in general, there's some additional challenges here when it comes to just character spacing and word spacing. Again, in English and a lot of other Latin languages, you use white space for the distinction between words, and we have punctuation to distinguish from one sentence to another. So character spacing, word spacing is pretty straightforward. But in some of the other examples here, Thai, Korean, Arabic, there's not always character spacing. There's no consistent character spacing in the Arabic script at the below. The Thai characters here does not have clear word spacing. There's a lot of variability across different languages, across different character sets, which means, again, this like one size fits all approach does not work for every language. As every language has its own challenges and its own unique properties that are different than English that make it a little bit more challenging. And so the point here is to be aware of those challenges, understand the language that you're working in, even if you don't speak it. I'm very monolingual, I only speak English, but I can still understand that languages are different and how they're different. And that helps me build a better solution when I'm trying to process and understand and take action based on the other languages and the data that I have. So with that, I want to turn a little bit to evaluating multilingual solutions. Because it's one thing to build a solution, but you have to make sure it works. So this is something I'm sharing some kind of lessons learned from my years and working in non-English languages. One is to value the importance of native speakers. Again, I'm hopelessly monolingual. I only speak English, but I really have to depend because of that on native speakers. When I'm building a solution, I need them to help me label data to make sure I have a train set and a test set that I can rely on and help me understand, why the model might be getting something wrong and where it's getting things wrong that I can't do as I'm not a speaker of that language. So that's really important as I'm building it and also as I'm testing these solutions. And then again, I've talked a lot about the biases and challenges, but know what they are and understand that, and also understanding, as I spoke about earlier, that a lot of packages and tools are biased to English and they're optimized for English. There are some languages and some packages out there that are designed for other languages. So maybe not as relevant anymore, but like back in the day, we used Spacie a lot for like tokenization and stemming and things like that. But there are other packages, open source packages, that are designed for different languages, such as when I was working with the Japanese client, we were using a tokenizer specific to Japanese. That was an open source Python package that we could use instead of Spacie. So know that some of those alternatives might be out there and they might improve your approach and your solution when you're working outside of English. And then the last part, which maybe is obvious, but I'm going to say anyway, which is measure your solution performance for each language that you're working in. So for essentially just stratify your performance measurements by language. If you just take an average, it's all going to average out, but your English might be performing really well, and then your Cantonese might not be, but that's hidden if you just look at the overall average. So you really need to understand that which languages might be performing better than others in your solution. So with that, I'm going to wrap up here in the next minute or so. But my kind of takeaway is pick the right tool for the job, and really, really just don't just throw an LLM at it and say it's going to be fine. Consider some of your other options like translation APIs. Don't use an LLM to translate at scale for an enterprise level AI solution. Translation APIs are faster, they're cheaper, and they're higher performance because that's what they're designed to do. So that's what I mean when I mean like pick the right tool for the job. And then again, just be aware that performance for LLMs can drop very quickly for non-English languages, and for the really outside the top 10 or top 20 languages, that performance drops off quite a bit. And sometimes that's published, sometimes it's not, but be aware of what that looks like if you can for the LLM that you might be using. And again, be cognizant that those models are primarily built on English data. So with that, I'm going to wrap it up. I think I maybe have time for one question if there are any in the chat. Okay, I'm not seeing anybody. I might also be looking in the wrong spot. I'm happy to connect on LinkedIn for those who are interested or have any follow-up questions. Please feel free to look me up. And with that, I'll hang it over to Newton for the second half of today's program. Thank you.
Rachel, I do have one question. Would you be able to answer it really quick?
I think Rachel dropped, so I will go ahead and start sharing my screen. All right, I hope everyone can see the screen. So today I'm going to be talking about FLAIR, which stands for Feedback Learning for Adaptive Information Retrieval. So what this means is basically how do we use users' feedback to improve retrieval over time in a RAG application? And the RAG application that I'm talking about specifically today is called DRI Copilot, where DRI stands for Designated Response Individuals, also known as on-call engineers. So DRI Copilot is basically a Copilot application for on-call engineers here at Microsoft, where they can ask questions in natural language. They can ask to summarize an incident, troubleshoot an incident, help them write a RCA report, or they can also ask questions on onboarding, etc. So I will quickly go over the backend or the architecture of the DRI Copilot. So RAG is really at the very core of this application. RAG also stands for Retrieval Augmented Generation. And the idea is pretty simple. We have a user who submits a question. The DRI Copilot or the LLM will take that question, rewrite it in a way that is more clearer with the intent. And then we use that rewritten intent to do a search over our chunked documents, and then it will get the top 10 or top K most relevant documents, give it to the LLM, and then formulate an answer and show it to the user. So that's essentially what the architecture looks like in very simple terms in this DRI Copilot. And in addition to that, we also have a feedback mechanism where a user can give feedback, which is basically a rating, a star rating from 1 to 5. Now, we wanted to see how do we use the star rating to improve the retrieval over time. So before we dive into that, first we will see how was the pre-processing done for this RAG in DRI Copilot. So we start with the data sources, which is basically the GitHub repository and the Eng Hub, which here at Microsoft is just a repository where people can contribute technical documents, and they can also have like common issues related to a product. What were the common troubleshooting steps taken for for those common issues? So, and basically, all sorts of technical documents are stored in these two primary data sources. Documents are then passed through a chunker, which will chunk these documents into smaller parts. And for each chunk, we basically create a JSON file which contains the title, the content, along with the embeddings of the title and embeddings of the content, which will then be used for doing a similarity matching and retrieving the most relevant documents. These JSON files or these chunks are basically stored in a blob store, from where the Azure AI Search, which is the Microsoft's tool, which is available on Azure portal, which can be used for retrieving the most relevant documents using cosine similarity or other similar metrics. Now, the motivation behind us doing this is that the Copilot that we designed was very effective in assisting with the on-call mitigation, but it still encountered regressions when it was no longer able to retrieve a particular document. So we often received user feedback where they said, "Hey, this was working in the past, but now it doesn't. I was able to retrieve the right document in past, and it was able to give me the right answer, but now it's not giving me the right answer." So to kind of tackle this, we wanted to see if we can use the user feedback that we have received in past to re-rank the documents in a way that we always fetch the right documents. So our overarching goal here, or the main questions that we wanted answers to, are how can we leverage real feedback to improve the DRI Copilot over time, or can we use any synthetic indicators to improve the search? Because in a production environment, getting real user feedback is quite rare. In our use case, I think we got real user feedback for about 2 to 5% of the queries, as we will see in later in the presentation. But there were a lot of challenges that we came across. Firstly, as I mentioned, the real user feedback was quite rare to come by. For our cases, we saw that only 2 to 5% of the questions had user feedback, and the feedback is rarely informative. And the other challenge that we came across is, what does it even mean for um, two questions or a question and a document to be similar? Because these are like technical documents related to proprietary Microsoft products. These documents contain knowledge that the LLMs or the embedding models have not been trained on. So even if two documents have a high similarity, it does not necessarily mean that those two documents are talking about the same thing. Here I present some basic historical analysis on the questions that were asked in DRI Copilot. So here the SQL DB and SQL DW are basically just two instances of DRI Copilot, which are deployed in two different teams at Microsoft. So for SQL DB, there were about 1,720 intents, or intents is basically just another word for user query. And for SQL DW, which was another instance of DRI Copilot, which was deployed for another team, we saw about 4,780 intents. Now, when we also performed some sort of clustering over these intents to find out whether are all these intents really unique intents, or is there any repetition? Like, are there any questions that users are asking repeatedly? So we did some clustering over these intents, and we found out that yes, there are half of the questions out of these intents or user queries were actually repetitive. So clusters of size 1 is basically, these are the questions or intents that were asked only once. Clusters of size 2 are, these are the intents or questions which were asked twice. Clusters of size 3 means they were asked thrice, so on and so forth. So we can see that there are about 50% of user queries which are being repeatedly asked. So there are, for both the instances of DRI Copilot, we see that there is a 50% distribution. There is 50% unique questions that are being asked, and then there's 50% where the questions are being repeated over time. And these are just some examples of questions which we saw repeatedly. So for example, what are the required permissions for a new hire? This question itself was asked 20 times in the DRI Copilot, which we deployed for the SQL DB team. And then mitigation for error 8501. This was a question asked repeatedly for the SQL DW team. And why it's important for us to do this analysis is because if we have repeated questions, and if we have feedback for even one instance of this question, we can actually use that user feedback to re-rank the documents the next time the same question is asked. And we'll see how that is done in the future slides. So here I want to build the intuition for the approach that we are going to talk about. Let's say we have a user question and we have 3 documents. The user question is just represented as intent here. We create an embedding of this intent. And let's say we have 3 documents, A, B, and C, and this is where they lie in the embedding space. So we can see that A and B are relatively closer to C as compared to C. So if we do a basic cosine similarity with this intent, A and B will be retrieved, and C will not be retrieved because it's relatively further away if we are getting the top 2 documents. But let's imagine that there is some positive intent signal associated with one particular document, and there is a negative signal associated with another document. Let's say that C was the DRI Copilot or the RAG application was able to retrieve the correct document C at some point in past, and let's say the user was able to give a thumbs up or a 4 or 5 star rating to that answer. In that case, we have a positive signal associated with C. So in this case, we want to design an approach such that if we have a positive signal to a particular document for a question that is similar to the current intent, then we want to bump it up in our when we retrieve the top K documents. And if there's a document that received a negative signal, then we want to bump it down. So using this approach, we'll be able to get A and C. But how do we actually generate these signals? One obviously is very straightforward. We use the user feedback. We use the ratings that the user have given us for those generated answers in past. So low ratings will, So the low ratings will basically fetch, a negative signal, and the high ratings will fetch a positive signal. But can we also generate synthetic indicators? And what we tried doing is we generated synthetic questions and answers, and then we associated positive indicators corresponding to those questions. So this approach, FLAIR, is divided into 2 parts. One is the offline or the pre-processing part, where we attach these historic signals as well as the synthetic signals to the chunks. And then there is the online part, which happens in real time, which enables us to re-rank the documents when the user asks a question. So this offline approach basically happens asynchronously. All of this happens before the user has asked the question. So as this is the same diagram from one of the previous slides. This is how the pre-processing happens. We have our data sources, we do the chunking, we have the document chunks, and we store them in a blob store, and then we can do the retrieval using the Azure AI search. But if we want to add some indicators to it, then we will have to add some additional fields into this JSON or the chunk that we have. So one chunk is basically nothing but a JSON file with all these different fields such as title, file path, content, etc. So let's say for our synthetic signals, we generate some synthetic questions from this particular chunk. And because we know that this question was generated from this chunk, we know that this is the right chunk for this question, and hence we can give it a positive signal. So here we have assigned it a signal of 0.5, and we have r hide QS0 is basically just the question that we generated from this chunk, and we have some keywords associated with that question, and then r hide sig 0 is basically just the positive signal 0.5 that we have attached. In addition to the synthetic signals, we will also assign the signals from the user feedback. So to assign signals from the user feedback, we query the Kusto database. Kusto is nothing but the name of the database that we use here at Microsoft. We do the mapping of user feedback to the chunks, and we do some filtering where we only consider the most recent feedbacks, and then we add that as well in our JSON or in our chunk document. So in the chunk, basically we will have the raw QS0, which is the raw question for which we received a positive signal in past. So for this, we will assign a signal of 1 because this is a real feedback. So we want to weight it a little bit higher than the synthetic signals or the synthetic questions which we are generating. Now we come to the second phase of FLAIR, which is the online phase, which happens in real time as the user is asking the question. So we have some source fields. Let's say the user asked a question Q, and then the intent is basically the LLM rewritten version of the question, which is more clearer. Then we compute embeddings of both the question and the intent. So these are our source fields. And we can compute the similarity with the chunks title, content, the embeddings of the title, embedding of the content, the title, uh, so the title vector basically just refers to the embedding itself. So we have all these target fields, and in our vanilla approach, we will essentially be computing the cosine similarity between the question and the title, the question's embedding and the title embedding, so on and so forth. Because we have so many different fields, we can also get different sets of documents. So let's say we compute the cosine similarity between the question and the title. We can get one set of documents just based on that one similarity matching. Then let's say we compute the cosine similarity between the question embedding and the title embedding, then we get another set of documents. So we can essentially get multiple sets of documents, and we can combine them using RRF score and get our final set of documents. But because we have our feedback signals and our synthetic questions that we have generated for each chunk, our set of target fields expands significantly. So that means that we can get multiple sets of documents depending on between what source field and target field we decide to compute the similarity. For example, if we take the question and the content, we can compute similarity using just these two fields. So we get one set of documents. Then let's say we take the embedding of the question and the embedding of the content. We compute cosine similarity. We get another set of documents or another set of chunks. So we can get multiple sets of documents. And the way to combine them would be using RRF score. Here, I want to talk about how do we use the user feedback or the signals that we generated in each chunk during the re-ranking stage. So let's say we have all these documents, we compute the score fields for the text. Between the text source field and the target field, we can use the BM25 score. For all the embeddings, we can use the cosine similarity score, and then we combine all of them using the reciprocal rank fusion. Using this metric, basically the documents which generally lied higher in these different sets of documents will be ranked higher. So let's say we did all of that, we got our set of documents, and this is our top 3 based on just the cosine similarity and the BM25 and the reciprocal rank fusion. Now we want to incorporate the feedback signal and the synthetic signal that we had generated. How do we do that? So the way to do that is by using um, by computing a vote score. Now, how do we compute the vote score? This is basically nothing but a weighted average of signals, or weighted by the similarity scores of prior queries. So here I'm going to take a dummy example to show how do we calculate that vote score. Let's say we have a chunk D or a document D, and we have a question Q1 for which this document D received a positive signal S1. Then we have another question Q2 for which this document D received a negative signal S2. Let's say our Q1 is how do I resolve crash loop backoff? And it received a positive signal by the user, positive feedback by the user. So our signal S1 is +1. For Q2, this document wasn't the right document, so we received a signal of -0.5. And let's say the current user input or the current user query is U, and our similarity threshold is 0.75. Similarity threshold is basically the threshold of the similarity between the user question U and the Q1 and Q2. So the idea is if the similarity between the user question and the past question is higher than the threshold, only then we will consider the signals in our vote score. Otherwise, we will not consider the signal. And this looks very math heavy, but I'll break it down for you guys. This is quite simple. Basically, we are simply computing the average of the signals weighted by the similarity scores. So CU is nothing but the cosine similarity between the user question and the question which was asked in past, which is Q1 and Q2 in this case. And this can be thought of as the cosine similarity. It is essentially 1/2 minus cosine similarity of these, the user question and QI, but we can think of this as a cosine similarity because this is just, we're just making the cosine similarity positive. So you can ignore this modification and just think of it as the cosine similarity. And based on the numbers in our dummy example, we compute the cosine similarity between the user question and Q1. It comes out to be 0.9. And the cosine similarity between the user question U and Q2 comes out to be 0.8. Both of these are higher than our threshold of 0.75. So we will use those in computing our final vote score. And when we multiply it by the signal, which is +1 for Q1 and -0.5 for Q2, we add them up, divide them by the total number of signals that we have, which is 2 in this case, we get a score of 0.25. So that's the vote score that we are going to use along with the RRF score for the final re-ranking of the documents. Now, in this slide, we will simply see the same set of steps that we saw before, but we are also going to incorporate the vote score that we just computed. And this big formula is essentially the same thing that we just saw in the previous slide. It's nothing fancy. So for our document C over here, we have a raw signal of +1 and a cosine similarity with the question of 0.98, which is greater than whatever threshold we had. I think we considered threshold 0.75, so we are going to consider that. And we multiply both 0.98 at 1 to get 0.98. Essentially the idea is that this particular document C received a positive signal for a question Q1 in past, and this question Q1 is highly similar to the current user question. Hence, we are going to incorporate this in our ranking, and we are going to consider this vote score, which comes out to be 0.98 because it's just one signal in this case. And then document A had a document A did not have any user feedback associated with it or any other signal, so we just consider it to be 0. And then B had a negative signal associated with it, which basically means that this document, for a question similar to the current user question, this document had received a negative feedback in past. So we want to assign it a negative vote score, which is minus 0.94 in this case. So we simply remove that because it has received a negative feedback in past. We don't want to consider it. Then we apply some additional filtering. We do the final ordering, and we come up with our set of documents that we actually wanted, which is A and C. I'll quickly go over the evaluation. How did we evaluate this approach of feedback learning? So for this, we considered a set of technical documents from a team called Azure SQL DB in Microsoft. All these documents are very proprietary and confidential. These are documents that the LLMs have not been trained on. So what we do is to create the evaluation data set, we use, I think for this, we used GPT 4.0. We asked GPT 4.0 to create synthetic questions and answer pairs from these set of technical documents, and we varied the temperature to get more diverse queries. And the metric that we used is recall. So for every synthetic query, we know what the source document was. So if our approach is able to get the correct source document, then we assign it a recall of 1. If not, then a 0. So in this case, it's the recall is binary, 0 and 1, but that's not how usually we have multiple documents, so the recall can be different, but in this case, it's just binary. Now, to do the evaluation, we performed an iterative learning simulation. In this simulation, for every iteration, we sampled 30 queries from this set of synthetic queries. Firstly, for the first iteration, we sampled 30 queries. From the second iteration onwards, we sampled 20 repeated queries and 10 new queries for every iteration after the first one. Then we do the whole computation of the scores that we just saw previously, where we are computing the we are getting the re-ranking by RRF score. We are computing the vote scores using the user feedback. We are doing the re-ranking again, and we are getting the retrieved set of documents. And based on whether we were able to get the right document or not, which we know because this is a synthetic data set, we assign a feedback of +1. If we get the wrong documents, we assign a feedback of -1 and -1. So we repeat this process multiple times. In the experiment, we used 200 iterations. So we repeat this process for 200 iterations. And the idea is that in the later iterations, because we have already seen, let's say initially it was only fetching the wrong documents, and we kept assigning it a score of -1, -1. In the later iterations, we expect it to get a better score. Like we expect it to improve and eventually land at the right document, eventually fetch the right document. So this was a simulation that we performed, and it was quite consistent with the production environment because we are also taking into account the repeated queries along with the new queries. Quickly, I think I have 1 minute remaining, so I will quickly walk over the final results that we got. After doing this simulation for 200 iterations, what we saw is that our approach, where we are incorporating, which here is represented by this brown rectangle, which represents feedback plus hike, basically means that we are incorporating both the synthetic signals along with the real user signal. And we are using a threshold of 0.75, which is basically just the what is the minimum vector similarity score between the current user query and the stored indicator query required for that signal to participate in the vote score. So this approach performed better than all the other baselines that we were considering, as we can see by the recall score. The rectangle showing the recall score, it achieved a recall score of 0.8 across all iterations. And even for both the repetitive old queries as well as the unseen queries. Even in the unseen queries, we see that it is able to outperform all the other baselines. I think there's one which is performing quite competitive. The hike one, which is performing quite competitive in the unseen new queries, but this approach seems to be performing quite well. I'll quickly go over what the other baselines are. The first is the blue one basically just represents a very simple cosine similarity match between the user query and the chunk title and content. The nudge is basically just a way to fine tune the embedding models, and the feedback 0.75 and 0.95 are basically the same approaches, but we are not using any synthetic indicators. So this approach also shows that the synthetic indicators that we created also added a lot of value in improving the retrieval. So I'm going to stop there, and I will see if anyone has any questions in the chat. So there are a few. Did you notice any bias in what types of questions users provided feedback on versus what they did not? The bias is there in the sense that we tend to receive a lot of either 1-star feedback or like 5 and 4-star feedback, because this is like user behavior, typical user behavior, where they are motivated to provide feedback if they really like something and if they really dislike something. So in our distribution of the stars that we were getting for the questions and answers, we saw a large number of 1-star and a large number of 4 and 5-star, and 2 and 3 stars were very relatively low. How do you know that the answers? How do you know that the answers that are given by the LLM? Are you asking how do we know that the answers given by the LLM are correct? So the way we know that the answers given by LLM is correct is because we were using the latest GPT model. I think at that time it was one of the GPT-4s, and we did like a manual audit with the subject matter experts to see that the questions and answers it is extracting make sense or not. Okay, I think that's pretty much it. Thank you so much. If there's any other questions, or if you would like the link to the paper, let me quickly add the link to the paper. And you can also reach out to me on LinkedIn if there are any other questions or any confusion or clarification needed. Thank you.
Thank you, everyone, for joining us today. If you enjoyed the session, please take a minute to fill out the survey and share your feedback with us. It really helps us improve future events. And also, don't forget to check out upcoming Microsoft Reactor events, and we hope to see you again soon. Thank you, everyone. We hope you have a wonderful rest of your day.